Hey there everyone, welcome back. So this video will be a derivation of the moment of inertia for a rigid rod. And we'll be using calculus, right, and integration techniques to determine the expression for the moment of inertia, okay? I wanted to state at the start that this is an optional video, right? I don't expect you to know how to do this for an exam, right? But just in case you wanted to know how those expressions for the moments of inertia are calculated for different shapes, I'm creating this video and then one more for a cylinder, just in case you're curious, okay? Again, it won't be required. Also, your book does have it in sample problem 10.07, but I don't think it's very well done. So that's another reason I'm doing this. All right, so what we have at the start is a curvy rod. Let's do it as straight as possible. All right, let's try that. So this is some rod of length L, total length L, and the center of mass is at the center, right? This means that the mass distribution is uniform, right? In other words, it's evenly spaced mass. It's even density throughout the entire object. So if we put the center of mass at the dot, right, that means that the mass has uniform distribution. And we call that lambda, right? In other words, the density is constant. So lambda is written as mass per unit length. So M over L. Okay. Later on, we'll turn L into X, but for right now, since lambda is constant, it's a total mass divided by the total length. All right. So let's calculate the moment of inertia if this rod were rotated about this axis along the center of mass. Okay. So I, remember, has the expression of mr squared. Well, we can now integrate for all of the distances, so r squared, throughout all of the masses. So I'll call this dm, right? And so this differential mass term really comes from all of the tiny bits of mass everywhere in this object, right? And if they're infinitely small, that means there are an infinite number of them throughout the entire object, and we can integrate all of these dm's to get the total. All right, so what we have initially is we need to turn this r, which is a distance, in terms of our problem. So, like usual, this r is the distance from the axis to where this mass is located. Well, in this case, let's do it in terms of x. Okay, so we have x squared. Right? It's just a linear distance, x. And dm, we don't actually know what that is, but we have a way to find what that is, okay, using lambda, the mass density, in other words. So solving for m, we have lambda times L, okay? And this is the overall mass. But what if we wanted a differential mass? Well, we take the derivative of both sides. dm is now equal to lambda. That doesn't change because that's always a constant, but the distance changes, right? The length changes. So this is a dl, but since we're using x, we can really call this lambda dx, right? It's just the position of all of the masses. So now I'm going to take this expression and plug it in for dm. So this is lambda dx now. And our integral becomes the following. The lambda can be pulled out of the integral because that's the constant mass density times the integral of x squared dx. Now, what are our limits to the integral? Well, we have a couple options here. We can integrate from one end to the other, right? In that case, it would be negative L over 2 to positive L over 2, right? Or we can multiply the whole integral by 2 and just go from 0 to L over 2, whichever way you want to do it. I'm going to do it from negative L over 2 to positive L over 2. Okay, and so what we have now is a lambda out front, and we have x cubed over 3 as the integral, right? Evaluated from negative to positive L over 2. So let's plug in our limits now and see what that is. I'll pull the 3 out as well. So we have L cubed over 8, that's 2 cubed, minus, let's see, a negative L cubed becomes a negative L cubed. And we have 2 cubed, that's also 8. Okay. And this becomes L over 3. We have, the first term remains the same. Now we have plus L cubed over 8. And so we have, let's see, that's 2 over 8, which is 1 over 4. So L cubed over 4. And this becomes like what is shown in your table. Okay, well, almost. Right? L, let's see. L times, sorry, lambda L cubed over 12. Okay, we're almost there. Now we need to plug in for what lambda is. Well, that's m over L, which leaves us m. One term of L cancels. That's ml squared over 12. And that's just what that table in your textbook or in one of my previous videos, that's just what it says for the moment of inertia about the center of mass of a rigid rod of uniform mass density, right? This is a very low fraction, right? 1 over 12 is relatively small. So that means that rotating this rod about its center of mass in the middle is pretty easy to do, right? So that's the derivation. Thanks for watching.